Welcome MAC1147 students. This is pre-calc and Trig. We're gonna go over our first practice test on a couple topics. So the first one is how to graph a piecewise defined function, right? So basically we have different functions on the coordinate plane based on the x values. So here we have, as you can see, something x squared plus c, right? This is a quadratic function. You should be able to look at it and say, oh, okay, that's a quadratic function. So you kind of have an idea of what it looks like. Right, for this bottom one, I see that it's a line because it's mx plus b, right? Slope and y-intercept. Either way, we're gonna make a chart and we're just gonna plug in points for each function, and then that way we can graph the ordered pairs and see what it looks like. Right, so for here it says all the values that are either equal to -2 or less than -2. Right, so we're gonna plug in -2, knowing that it's gonna be a closed circle because it is a point on the function, right? You're allowed to have -2 as a solution. So you are able to plug it in, and also any values smaller than that. So we can plug in -3, -4, and that should be good enough. I would say at least 3 points. 4 is ideal, but 3 is good. Okay, so for the bottom one, we are going to plug in -2 as well, but we know that it's an open circle because technically it's not part of the function. It'll just be a reference point to see what happened. Was there a jump? Was there a sharp turn? Something happened where the function broke into 2. So we'll also plug in some more values that are greater than -2, so that could be 0, 1, maybe I'll do 0 and 2 since I'm doing even numbers. Okay, so now we just have to plug in. So we'll plug in the -4 and make sure that you use order of operations. Right, so here we have -3 for the top function, x squared, where x is -4, and then you just have to plug in this all. Right, so of course exponents before multiplication. Here we have -4 squared, which is 16. Times -3 plus 1. So that's going to be -48 plus 1, -47. So that's going to be kind of hard to put on the number line on the coordinate plane. But remember, we can always use a different interval that's convenient for us. All right, let's plug in -3 as well. We'll just keep on plugging in to the top function. All right, this is -3 squared, which is 9, right? -3 times -3. And then multiply that by the -3 in the front, add 1. All right, so you could do the math, verify with me that it's -26. Okay, so far so good. All right, remember it's a video. You can go back, pause, watch again. Okay, so here we have -3, -2 squared plus 1. -2 squared is 4. That's just -12 plus 1, which is -11. Okay, so these are some ordered pairs for my top function, which should be part of a quadratic function. All right, for the bottom is just a line. Plug in some more points. So let's plug in -2. Then we'll plug in 0, which is always a good one to plug in. All right, because that will be your y-intercept. And plug in 2. Okay, so for this one, we get -12. -12 minus 8 is -20. Here we have 0 times 6, which is 0 minus 8 is -8. And then here's just 6 times 2, which is 12, minus 8 is 4. Okay, great. So considering that I have these values 4, 8, 20, I'm going to do intervals of 10, right? Because we want to be able to graph this. So let's do intervals of 10. Well, on the x-axis, I'm going to do intervals of 1 because I plugged in values that are close to each other, right? So it's going to be better for me to use intervals of 1 for the x-axis. That's fine as long as you're consistent. So I'm going to do intervals of 1 for the x-axis and intervals of 10 for the y-axis. Totally fine. Whatever is going to help you be able to graph this piecewise defined function. Alright, so for this one we have -4, comma, -47, so that would be close to -50, there you go. -3, comma, -26, close to -30, -2, comma, -11, but it's an open circle, right? So -2, comma, -11 will be right here. Alrighty, so connect these dots, okay, you should be like part of a parabola, right? Half of a parabola, so you can see. All right, then from there, we have the next function, which is a line. So that's going to be -2, comma, -20. but it is closed circle. 0, comma, -8. That's close to -10. And then 2, comma, 4. 2, comma, 4 would be a little less than half. All right, you could do some more points, but you know this is a straight line. All right, let's make my points a little bigger. Okay, and that's gonna keep going on forever because as you can see, you can plug in any x value greater than -2. So keep on going, you'll get more points. The line will keep extending forever, right? Same concept with the parabola, goes forever on the left because you can keep plugging in negative values lower than -2. Okay, so that's it. That's our piecewise defined function. For the next part, we are going to evaluate at certain points. So it's asking, what is f of -4? In other words, when you plug in -4, what do you get? We actually already did that. F of -4, we got -47. All right, so I got my answer. And then what is f of -2? We also did that, but remember you want to go with the closed circle one because this is the actual closed point on the piecewise defined function. All right, so it's going to be the closed circle, -11. Okay. All right, so that's number 1. That's piecewise defined functions. All right, number 2. Alright, so for this one, we have a polynomial function, and we're going to find the zeros, okay? Always try to find the zeros, which are the x-intercepts. By setting y equal to 0, and then try to factor yourself, okay? So if I set this equation, f of x is y, right? It's all of your outputs. So if I set y equal to 0, then I can solve for x. Okay, so we're solving for x. We're going to try to do this by GCF, factoring, quadratic, whatever you can to solve. Right, so I see that they all have an x in common, so I'm going to take an x out. And what is that going to leave me with? It'll leave me with a -x squared. Actually, I'm also going to take out the negative because I personally like to have the coefficient as the coefficient that's going to be left over. The trinomial that will be left over, I like to have it as a positive number, but you don't have to. So either way, you're going to get the same answer. So I'm going to go ahead and take out a -x because clearly they have a negative in common. Okay, so if I take out a -x, I'll be left with an x squared, a -8x, and a +60. Right? I can check my work. All right, now let's see if we can factor this. And yes, of course you can. We can split x squared as x and x, 16 as 4 and 4. Because it's positive, we're going to either make both factors positive or both negative. We're going to make them both negative because you're trying to get to -8x. So this is going to be outer, -4x, minus, and then inner, another -4x. So we did kind of do this, we did do this correctly, okay? So we just factored it, this is great. All right, so now we can solve for x. Right here, when we split this up, we get that -x is equal to 0. So clearly x equals 0, right? Just divide by the negative in front. And over here, we're gonna get that x equals 4, but we're gonna get a multiplicity of 2 because we're technically getting that answer 2 times, right? Over here, we only get this multiplicity of 1. This is helpful because we're gonna graph this polynomial. So we want to know multiplicity. There's a chart that we can use that tells us, okay, you're going to touch the x-axis or you're going to cross the x-axis. And this is a faster way to graph without plugging in a bunch of ordered pairs. But when in doubt, you can always plug in an ordered pair if you're trying to see, okay, at this point, how long should the term be? So we'll see. That's that. Part A. Okay, so for part B, we're going to state the end behavior in order to graph this polynomial. And so you can use the chart, right? So the chart says all you have to do is look at the highest power of the polynomial, right? That's called the degree of the polynomial. So I see here the degree. Wow, just had a moment there. The degree is 3, and the leading coefficient is the number in front of the highest power, so that's a -1, right? So according to this, you use the chart, and it says that if your degree is odd, which it is, and your leading coefficient is negative, then let's grab this. Let me go back to the better one that I had. There you go. Odd, negative. All right, then it's going to be going up to the left, and it's going down towards the right. All right, so let's do part C now. Part C is to graph this polynomial. So we're going to graph. What we're going to do, we're going to always graph your x-intercepts, right? So we got 0 as an x-intercept, and we got 4 as an x-intercept, right? And the end behavior says that as the function goes towards -infinity, right, towards the left, it's going to go up forever. And as you go towards infinity, the function goes towards infinity, all the x values to the right, it's going to go down forever, right? So that's that. So then now all we have to do is figure out what happens from this point to this point. Okay, and that's why the multiplicity is important. So for here, this is x equals 0, right? We got a multiplicity of 1. So now we're going to use the multiplicity chart. So let's go to it. All right, and I did send a picture of this. You can also look it up on Google. All right, so it says that if you have a 0 with an odd multiplicity, then the graph crosses the x-axis. Maybe I should do it over here. Crosses the x-axis when it's an odd multiplicity. All right, when it's an even multiplicity, it's gonna just touch the x-axis, but it cannot go through it, and it's gonna change direction. So even multiplicity, you're gonna just be able to touch the x-axis. All right. So at x equals 0, it was an odd multiplicity, so that means you're gonna cross the x-axis, which means you're gonna go through the x-axis, so it's gonna go like this. Now we don't know exactly how far down it's gonna go, so in a moment we're actually gonna plug in a point and just verify. Okay, but as you're getting to 4, that has a multiplicity of 2, remember? We had gotten it twice. So if it's an even multiplicity, then you're going to touch the x-axis. So this means that as it goes back towards it, it's going to touch it. Maybe I should do it a little better. There you go. It's going to touch it, but it's not gonna be able to go past it. Right? So now let's see what happens here, because we don't know how far down this is or how far up it is. So let's plug in maybe 2 and see what we get. Okay, so let's plug in f of 2 and actually get the ordered pair for it. Alright, so this is 2 to the third power, which is 8, and then make it negative. This is 2 to the second power, which is 4, times 8 is 32. And of course, negative 16 times 2 is negative 32. So this is going to cancel, and you're going to get 0, negative 8. Actually, that was one of our, we already erased it, but anyway. So 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be up to down here. So let's fix that. Alrighty, so that's our rough draft of this polynomial using the charts that we were given. And here we should try to make this just a little bit more rounded so it doesn't look like such a sharp turn. So I'm gonna go touch the x-axis and then go back around. Alrighty? Awesome. So that's number 2. Alright, number 3 is pretty fun in my opinion. is just long division and synthetic division dividing polynomials. So those are the easy points. Alright, so by long division, it says, can you divide 2x cubed, I'll just write it, 2x cubed, divided by 2x minus 5. Okay, great. So we've done these in class before. So here we have 2x cubed, right? We're going to try to divide 2x cubed by 2x and see what needs to go in the quotient. Quotient is your answer. Alright, so if I divide 2x cubed by 2x, I'm just going to be left with an x squared, right? So this is going to be x squared. Alright, but don't forget that there is an extra term here in -5. So that x squared that we chose as part of the quotient, it's actually distributed to the 2x minus 5, both terms. Right, so this is where the 2x cubed comes from, the one that we're trying to cancel out, and then a -5x squared. Now remember, we have to subtract both of these because this is division. So we're going to take away the 2x cubed, right, which is going to cancel it, and we're going to subtract -5x, which is adding 5x squared. Okay, so that's going to give us -4x squared. And then, same concept, we're going to divide the next leading term by the first term of the divisor to see what we need to continue to add in the quotient. So here we have -4 divided by 2 is -2, and then x squared divided by x is just x. So it's -2x. Alright, that's what we're picking. Now that -2x is being distributed with the divisor. And so let's see the extra term that is part of it as well. So it's going to be -2x times 2x, which is the -4x squared that we're trying to cancel out. And then -2x times -5 is positive 10x. Okay? But don't forget that we're subtracting both of these terms. Right? They're split into two terms, so subtract both terms. So this is actually adding 4x squared, which cancels it. And this is subtracting 10x. Okay, here I'm just going to add 0x because you don't have an x term. You don't have to do this, but I like to have the term there so I know what to take away from it. Okay, so the next term that we have when we take away 10x from 0, which is -10x, we are going to try to get to -10x. Alright, so you repeat the process until you're done, right? Or you have a remainder. So -10x, we're going to divide by the 2x in the remainder, see what that number has to be. Alright, that number in the quotient is going to get distributed with the divisor. Alright, now remember that both of these are being subtracted, both terms. So this is actually going to be adding 10x and subtracting 25. Right, so if we add 10x here, I'll go this way so you can see. This is going to cancel, and then bring down the 15. You're going to subtract 25 from 15, which will leave us with a -10. Right, so we have a remainder of -10 over the divisor. Right, so this is our answer, our quotient. We got 3 full terms, and we have a remainder of -10 over the divisor. Okay, great. Now, perhaps you prefer synthetic division, and synthetic division is recommended in terms of finding zeros of the polynomial when you have a super long polynomial. It's going to be faster. Okay, so we're going to do a different problem with a different method. It's basically the same thing, we're just not going to put all the variables in it. So here we have give me a sec. I'm gonna change this problem. Alright, so here we have, it's all in different order, right? So we want to get the highest degree. So the highest degree here is 4, so it's x to the 4th. So we have a coefficient of 1, x to the 3rd has a coefficient of -3, and so on. X squared 1, x is 4, and the constant is just -5. Alright, so synthetic division is used when you have a divisor that's x minus c, right? So when you have a divisor that's x minus c, you set it equal to 0 and you solve for c. Okay, and that's the c that you put over here that you're going to divide by. So for number 3b, I should have put x minus 2. Let's make that negative x minus 2. So, okay, we'll do x minus 2. It's fine. We're just gonna solve for x. So we're gonna add 2. So we're gonna have 2 as our c. Okay, and then we're just gonna apply the steps. So you can bring the first number down. You multiply 1 by 2. You get 2. Add these numbers inside the box. So it's gonna give you -1. Now -1 multiplied by the 2 on the outside again, and -2, add them, left with -1. -1 times the 2 out there is another -2, add them. 2 times the 2 out there is 4, add them, and you're done. Right, so then for your answer, what is it going to be? Well, now these terms are 1 degree lower because you're dividing by an x variable as well. So is it going to be 1x cubed minus x squared minus x plus 2, and this is your remainder. We usually put a box around it. So this is your remainder over the divisor. Remember that the divisor is x minus 2. Okay. Awesome. Let's say that your divisor was negative x minus 2. It's fine, you're still gonna set it equal to 0, solve for x. So add 2, negative x equals 2, divide by the -1, divide by the -1. So you would plug in -2 into the c if that was given. So basically, if you ever have a divisor that's of the form a variable and a constant, plus or minus a constant, set it equal to 0, solve for that c, and that c, that number, is the one that you're gonna put on the outside of the synthetic division box. So I'll update that. Okay, number 4. Okay, so part A says find the zeros. So normally when you finding zeros, that means find the x-intercepts, right? So in other words, set this equation equal to 0, solve for x. So I can see that even if I tried, well, we can try. Let's try to do factor by grouping, because if factor by grouping works, then we don't have to do synthetic with a bunch of different possible zeros. Okay, so let's see if it works. So here I have a 4 in common, right here. Both of these are divisible by 4. And they both have x squared in common on the left. What would that leave me with? That would leave me with an x minus 1. Awesome. Okay, so this is going to work. On the right hand side, what do these have in common? Well, they're both divisible by 25, and they have a negative in common. What would that leave you with? That would leave you with an x minus 1. So factor by grouping does work because this binomial is the same. So your final answer is going to be your first GCF joins with your second GCF and then your binomial one time. Okay, so we're able to do it. And of course you have to set this equal to 0, solve for x, and those would be your x-intercepts. Alright, so let's set the first one equal to 0, and then we'll set the second one equal to 0. It's easy to solve, and this is just going to require some work. Right, I'm adding 25, then I'm going to divide by 4. We don't have to cancel out opposite operations. So this is that x squared equals 25 over 4. And then of course what's the opposite of squaring? Square rooting. So you're going to use the square root method. Square root the right hand side, and remember you have a positive and negative answer. So it's going to be x equals plus or minus 5 over 2. Because the square root of 25 is 5 and the square root of 4 is 2. So you can actually break up the square roots on the numerator and denominator, solve for it, and it's actually a pretty answer. Okay, so that means that if we didn't do factor by grouping and we wanted to do it by doing P over Q, seeing the possible zeros, we would have had a bunch. And the ones that would have worked would have been the negative 5 over 2, 5 over 2, or 1. So hopefully you would have picked one of those, but it would take some time because you have so many possibilities. So of course, try factor by grouping. If it works, awesome. It's going to be faster for you. If not, not a big deal. Just try out some of the possible zeros and eventually you'll get it with synthetic division. Alright, and then part B is, can you write this polynomial in factored form? Yeah, that's not a problem at all. I know my zeros. So I'm gonna put my zeros over here. I got x equals 1, x equals 5 over 2, and I got x equals negative 5 over 2. Alright, how do we write this? Well, there's the factor theorem that we spoke about that says if you found a zero of the function, in other words, f of c, where c is that 0, and you are getting a remainder of 0 in the synthetic division, in other words, it is on the x-axis, then that means that x minus c is a divisor of the polynomial. In other words, this is going to be factored out and we're going to get, well, let's go back to it. So we actually had done factor by grouping, right? It was 4x squared minus 25, and this is x minus 1. Okay, so a couple things to tell you. So first, we actually did factor by grouping, so we could have actually used this as our factor form, but of course this guy, we could continue to factor it, right? So if we were to factor this guy, it's actually perfect square. A difference of squares because it's subtraction. So 4x squared we could split as 2x and 2x. 25 we could split as 5 and 5, right? It's a perfect square. And then, because it's negative, you're going to make one negative and one positive, right? This is going to ensure that when you do outer and inner, you have no inside term, right? So this is the factored form, right? Because you factored all the way, the factored version of the polynomial. Okay, let's say that you didn't do factor by grouping, and instead you did synthetic division to find the zeros, and you found them. You got 1, negative 5 over 2, and 5 over 2. Not a problem. According to the factor theorem, x minus c is a divisor of the polynomial. So in other words, it would be x minus 1 times x minus 5 over 2 times x plus 5 over 2. Because remember, it's x minus c, so since one of them is negative, it'll be minus a negative, which is addition, right? So this is also the same thing, factored form. Just instead of writing it as 2x plus 5, they've written it in a different form and solved it for us, right? Okay. If you're skeptical and you don't believe that, well, then just look at the 2x plus 5. Remember that when we set 2x plus 5 equal to 0 and we solved, we got negative 5 over 2, which is this C right here. And same concept here. Okay? Perfect. Okay, number 5, use a rational function to answer questions. Okay, great. So remember, they always want to, this is a rational function, right? A polynomial divided by another polynomial. You always want to factor first and see if anything cancels out, okay? So on the bottom, I see it's the difference of squares, so that's going to be easy to factor. X squared will split as x and x, and 1, factors of 1, 1, and 1. Because it's negative, we're going to make one negative and one positive. Awesome. For the top, we're going to try to factor. Alright, x squared will split as x and x. And then the factors of 8, we have 1 and 8, or 2 and 4. I'm going to try 2 and 4. Of course, if that doesn't work, you can always change the factors. Okay. For the last, I'm going to use the factors of 2, which we have 1 and 2. Okay, because it's negative, we're going to make one negative and one positive. Again, we're going for it. If it doesn't work out, we can always change it. So here, let's check outer and inner. So if we do outer here, we get negative 4x. We do inner here is plus 4x. That would be 0, so that was not it. All right, let's swap it. Let's put the 2 here and the 1 here. All right, now let's check outer and inner. So here we're gonna get negative 8x for the outer plus 2x for the inner. That's negative 6x, so that's very close to the 6x that we need. That just means that these signs have to be switched. I can leave the numbers there now, but if we switch the signs, it'll give us the 6x that we're looking for the inside term. Okay, so once you've done that, it's always beneficial. You're gonna see if anything cancels out with the top and bottom. So here I see nothing cancels out. Alright, if it canceled out, that means that that's a hole in the function. But right now we don't have any holes in the function. So that means that these denominators are going to remain in the denominator. Okay, in other words, for part A, is there a vertical asymptote? Yes, there are actually 2 vertical asymptotes, because you're going to set each of the denominators that didn't cancel equal to 0, and we're going to solve for it. Right, these are both of our vertical asymptotes, right? So if you were to graph, which we're not going to graph this one, you would have a vertical line at 1 and a vertical line at negative 1. Let me make that better. Okay, so that's vertical asymptote. For part B, it says, is there a horizontal asymptote? Well, we would use the chart. So the chart says, which I already know, the chart says that you're actually going to use the degrees of the numerator and the denominator. So the degree in the numerator is represented by n, and the degree in the denominator is represented by m, right? And based on n and m, you use the chart and see if there's a horizontal asymptote. So for here, because they are equal to each other, you actually divide the coefficients in front of the highest power. Right, so that would be this 8 divided by the 1, and that is the equation of your horizontal asymptote. So this is going to be y equals 8. Alright, so up here it would be 1, 2, 3, 4, 5, 6, 7, 8. That's your horizontal asymptote. Now we're not going to graph this, but if you did, what would you do? You always want to pick some points to the left of the vertical asymptote. So here you will pick some points to the left of the x equals -1 horizontal asymptote. You want to pick some points in between them, and you want to pick some points to the right of it. That way we can see what's happening in each region. Alright, it gets interesting. You could have a cubic function somewhere, and then you have other functions in different spots, right? So very interesting question. For part C, it says determine if there is a slant or nonlinear asymptote. So we've talked about it before. If there's a horizontal asymptote, there is no slant or nonlinear asymptote. So for this one, we're going to say no slant or nonlinear asymptote. How do you find the equation of the slant or nonlinear asymptote? You just do long division, which we already reviewed. And the pretty part of the quotient, right, the part that doesn't have the remainder, is the equation of the slant or nonlinear asymptote. Remember, slant asymptote is a line, and nonlinear would be any other nonlinear function, such as a parabola. Okay. Now part D is a bonus question. It says, does this function cross the slant asymptote or nonlinear asymptote? Well, no, because there is no nonlinear or slant asymptote, but this would be a great question if there was one. How would you do it? You would just set the function equal to the equation of the nonlinear or slant asymptote. And then you do algebra and you solve for x. Okay, just make sure that you get x equals a number. Okay, that would tell you the ordered pair, the x value of the ordered pair that is crossing that asymptote. Okay, so with that, remember that if you get, like for example, you do have all the algebra and you get 4 equals 3, that's not true. So in that case, it would be no, this function does not cross the asymptote at any location. All right, so last question. Okay, so now we're going to solve this inequality. All right, so remember that first you need to have this 5 moved to the left-hand side. Okay, why do we do that? Well, because we need the inequality sign to be next to 0, right? We need to know, okay, do you want it to be less than or equal to 0, greater than 0? Okay, so we should always have 0 on the right-hand side before you start solving for x. Okay, so here I see, okay, I have a fraction, and then here I have a number that I'm trying to subtract. So I'm going to have to find a common denominator between 1 and x minus 10. Remember that x minus 10 is just some number. So I'm going to use x minus 10 as the common denominator. Alright, which means that the first one is staying the same. And for this bottom one, it's changing, right? So if I multiplied 1 by x minus 10 to get x minus 10, I also have to multiply the number on top, which is a -5, I'll do it on the side, by x minus 10 and see what the numerator is going to be. Okay, so multiply it out. And that's going to be your numerator. Okay? I just distributed the -5, so it's -5x plus 50. Okay, so now I see that I can join these like terms, right? 3x minus 5x is -2x. Okay, so then I end up getting this rational function. Okay, almost there. I'm going to go to the right-hand side. Okay, so now we're going to set both of the numerator and the denominator equal to 0. We're going to solve for x and use those as our boundary points on the number line. Okay, so I'm going to set the numerator equal to 0, solve for x. algebra, we don't know how to do this. So 25 is my boundary points. And for the other one, x minus 10 equals 0. So of course that means that x equals 10 is my other boundary point. Okay, so now I have to plug in some points in the intervals between those boundary points. So I could pick a number to the left of 10. I'm gonna pick 0 because that's an easy number to plug in. A number in between, I'll pick 15. It's not a big deal. And then over here, a number bigger than 25, I'll pick 30. Okay, you can pick any number, of course, as long as it's between the intervals. So we're gonna plug in 0, 15, and 30 into the original function, well, into this one, because this is the one that we made sure that we subtracted the 5 before we started solving. All right, so we're gonna plug into here and see if we're gonna have a positive or negative value. All right, so let's plug in 0. Alright, so this is going to be 0 over negative 10, which is just 0, minus 5. Alright, so that's going to be negative. Okay, when we plug in 15, let's see what happens. Again, you just need to know if it's going to be positive or negative, right? So this is going to be 45 over 5, which is 9. And then my 9 minus 5 is 4, so this is a positive region. And then we'll plug in the 30. Alright, so this is going to give us 90 over 20, right, which is 9 over 2, or 4.5. So that's going to be 4.5 minus 5, which means it's going to be negative. So this is negative region. Okay, why is this important? So if this was graphed for you and you were asked, where is the function less than or equal to 0? Then you would be able to say, oh, it would be possibly at the boundary points on the x-axis. You would see, are there any points on the x-axis that are allowed to be there? And then are there negative y values, which would mean that they're below the x-axis, right? So in this case, they're asking us less than or equal to 0. So these boundary points, they always start off as open circles, but we can close them as long as it doesn't affect the domain, right? So for the domain, if I were to plug in 10 into here, I'll get 10 minus 10 in the denominator, which is 0. And that means that it's undefined, it's an error, right? So I'm not gonna be able to close the 10, but the 25, I have no problem closing it, because if I were to plug in to the function, I'm not gonna have an error. I'm gonna be able to get an answer, right? So this is the only one that I'm allowed to close. Okay, so that means that for where is this function either equal to 0 or less than 0, it'll be at the negative region. So it'll be right here and right here. How to write that in interval notation? Well, these are all the negative numbers, right? All negative infinity, keeps on going all the way to 10, open circle, parentheses, union, pick it up from 25, it's a bracket because that is a closed circle, and you're going to get all the way to infinity because any positive number greater than 25 is in fact going to give you a negative y value. In other words, it'll be below the x-axis. Okay, so we don't know what this looks like, but we're able to figure out where the function is less than or equal to 0 by finding the x-intercepts. Once again, you can always find x-intercepts pretty much. And then from there, seeing, okay, let's test some points and see what we get for each region. Is it positive or is it negative? Okay, so that's it. This is a review, quick review of practice number 1. So this is a little bit of everything from a little bit of chapter 2 and some of chapter 3 from our book. Okay, so take care, review, study, and I'm sure you're gonna do great.